So this is like actual aircraft which I was talking. This gets lifted. This comes like this in the while landing, while takeoff or while in the cruise condition. It is flap down spoilers. And these are flap tracks or pylon. And sometimes these are flap tracks basically and pylons. Few aircrafts have smaller, it's a single engine, so these are combined. Then your leading edge, we call it as a trailing edge. This is a winglet, which provides additional efficiency. It's good to have. It's not necessary. Like few aircrafts won't you won't see a winglet at all in the future, but this is even a structural member, because only in order to have an efficiency, increased efficiency, it reduces the drag and increases the lifts. This is the like tail cone, your vertical stabilizers, horizontal stabilizers. This is the actual picture how it behaves. Now this is very interesting. Like a structure analyst should know what is monocoque and semi-monocoque structure. So for example, this, if I have to design something like this, semi-monocoque, then it is easy. If I have to design like this, where you have only skins and small sections of the frames. So in this case, if it is the fuselage is pressurized, if this is pressurized from inside, actually the aircraft is pressurized from inside for human comfort. So they will either uh, shrink or it will explode. So in order to avoid that, we have to make it a beefy structure. The thickness of the skin should be too high. Here, what they did it is, here you see there are small, they call it as a stringers, or you call it as stiffener. I want to say technically it should be stiffener, because it is going to provide stiffness to your skin. The thinner skin, along with the small, at a frequent interval, you provide the stiffness to the skin so that it won't buckle or won't explode. And these are formers, or frames, basically to maintain that shape. Else the shape will be destroyed. It will buckle or explode. And the bulkheads to separate the sections. Like this is the tail section. Here you won't need any pressurization, because there is no human comfort or something like that. So that is the drastic difference. If I want to design this structure now, if this is solid throughout the solid, like throughout the solid skin, this I can use sheet metal. This I can't use sheet metal. So this will be beefier or heavy, bulky, and this will be lightweight design. That is why generally you use semi-monocoque or shell structures rather than the beefy monocoque structures. That's what I covered, like most of them. So okay, now this is like in structures also we have basically three classifications are primary, secondary, and in secondary there is category A, B, and C. So for example, winglet, we call it as an category C structure. It is good to have, but not required. That is called as category C secondary structure. So in primary structure, those are mandatory. You cannot avoid. Cannot avoid. Without skin, aircraft won't be pressurized or won't even it fly, because your aerodynamic drag is disturbed, your flow is disturbed, drag is disturbed. Everything will move out of the aircraft. Spars or spars which are attached in the wing from leading edge or trailing edge, the wing will buckle. Everything, stringers, stiffeners, longerons, bulkheads. Without this, the aircraft can't fly. This is mandatory and it is required. The safety is required for that. And secondary structures, okay, even if um one or even if the function, if one of the spoiler fails of this aircraft, there are like multiple spoilers. You see one, two, three, four. Even if one of the game gets damaged or something like that, it's fine. It's okay. Nothing is going to happen drastically. You can carry one flight. They will allow you flight with a payload. But this is what secondary structures majorly to enhance the aerodynamic or to provide the lifts, change the bonding, say change the conditions of the aircraft, betterment of the aircraft, like fairings, frames, wingtip, spoilers. You see wingtip secondary structures, spoilers, ailerons. Now this is a typical cross section of the fuselage. So I will explain you everything except wirings you see over here is everything is structured. Even if you drill a hole to install a wire to go through this any of the frame or stringer, you have to analyze it. So that's why I said nobody can customize the I'm going to say structural part of the aircraft. You can have customization in the seat. Somebody can have 20-inch TV in the aircraft rather than 16-inch or 12-inch, but no, you can't change anything. Like this cutouts, you can't do it anything. These are the structures. These are the main load carrying member for the aircraft. So these are the stringers which I told you long running throughout the cross section of the aircraft like this. Running. This is like throughout the cross section. Sorry, throughout the section of the aircraft. And the frames will be running circular. Suppose this aircraft is going through withstand like n number of loads. So if it is going to bend in this fashion, then the stiffener avoids it. If it is going to buckle or shrivel, the frame avoids it. Which are these structures? The frames, stringers, and this is now if you see, this is a thinner part, but it is stiffened panel. So it is going to withstand more load when compared to if you don't have this kind of structures. You have only monocrack structures. That is the reason we go with the semi-monocrack structures. These are the bulkhead frames which are more beefy, because if you see there may be landing cutout or something cutout area, then we have to have a beefier frames. That is why we call it as bulkhead frames or bulkhead. So this is a typical section of a wingtip to wing joint. Wing joint, wing to fuselage body joint. So this is the wing center section. Basically here your wing comes over here. So this is basically a cantilever. You see, it is a free and it is a body joint. If I take a mirror image of this, and if I it is fixed at the center at this location and loaded UDL and various type of UDL, dead load, fuel load, self weight, everything. So all this analysis should be taken care by the structural analyst. These are like a typical section of the wing. Now this is wing. Suppose you have a load like this, and if you have a small thin skin, it is not gonna um, avoid the failure of the wing. So what you do is, okay, in order to maintain the aerofoil shape of the wing, you install the ribs, which will help the skin to maintain the aerofoil shape of the wing skin ribs. Now, in order to, since the wing is acting as a cantilever, so it is going to be lifted in and out of the paper in during the landing, at the landing, because of the engine load and all those stuff. So this should provide the stiffness. So that's the reason you have the spars, front spar, rear spar. And if for the bigger aircrafts like A380 or A350 or 787, which are a bigger aircraft, which are generally used for long flights, we have a mid-section spar also, because it is the spar length is more, the structure, the engine weight is more, and fuel weight is more. So in order to that, to compensate for that loads, we have three spars rather than two. Now these are now the trailing edge. Now here your control surfaces are at the back end, which is fitted again on the rear spar, and the control surfaces on the front, which are fitted on the front spar. So this two spar, front and rear spar, are two beefy structures in the wing. Like the weight of the wing without these two spars is like 50%. These two spars carry the 50%, and of course excluding engines. Engines are like beefier, like anything else. So that is how it is designed. Then you have ribs. I mentioned you earlier. This is a typical section of the stabilizers. It look like similar to the wing structure, but here you don't have what we call predominant weights like engine weight or fuel weight. So this structure is less beefier than your wing. It is similar to your wing, but a vertical. Similarly, you will have a horizontal stabilizer, and in verticals, I'm going to say in horizontal stabilizer, you see the same structure. It will be the same structures, except here you will have a control surfaces which will allow you to change the direction of the aircraft pitching, and in the horizontal it will be nose down, nose up, and yawing. That is the, and it's that the name, it says stabilizer. If you don't have this, how you will stabilize the aircraft? Will you will have a yawing condition will be restricted, your pitching conditions will be restricted. That is the reason it is called as a stabilizer. Now, the most important thing is like for a structure analysis is to know what are the loads coming on the structure. You can't analyze a structure without knowing what are the loads. So, what are the sources of the loads? Like external pressure or aerodynamic. I would say aerodynamic group will have their own aerodynamic drag and thrust loads. Then I said concentrated loads due to the impact first strike damages, or we consider that also. Then control loads. If you go through hailstorm, there are a lot of times the hailstorm happens in the bad weather. So the aircraft should be there should not be damage to any skin. Since the skin is very thin structure, it's very thin. The self weight of an aircraft, self weight of the components. Then for fuselage, again, you have internal pressurization because the aircraft is flying at 35,000 feet and you want the comfort level of 5,000 or 6,000 feet. All the passenger wants. The lower, I'm going to say, the lower atmosphere, I'm going to say, the lower height comfort everyone wants, because at the greater height, it's difficult to breathe. It's difficult to stay longer hours with the dehydration, and all the stuffs will occur. So that is the reason we have a pressurized cabins, and to provide the passenger comfort, and the passenger can stay longer duration during the flight. Then thermal loads, like basically these are predominant case of composite. When you have composite to metallic joint, something is made of a composite. Suppose wing skin is made of a composite, and spar is made of aluminum. AL. So you have a joint. The thermal expansion of composite is very less, and thermal expansion of AL is very high. In case of a hot dip cases, the spar will expand at a rapid speed when compared to your skin. That will induce thermal loads. So all those criteria, engine thrust developed by the engines which you are going to put, then gust loads like turbulence and all those stuff. So this all are the sources which will provide the loads. Now the forces, these are the boundary conditions which you put it into the wind tunnel. Then you apply the strain gauges on the structures, and you get into the what are the strains. So strains can be like anything, like compression. Strains are basically three: compression, tension, and shear. And then you have a moments because of longer heights or longer length of the aircraft, or cantilever beams and all those stuff. So this ground loads and air loads, which ground loads like moving, I would say landing during the landing, or while landing, um, or taxiing, towing. For example, you have a dead aircraft sitting with the fuel completely loaded, then it has its own ways and all those stuff. We call it as ground load. And air load, like it's as soon as its engine gets on, and um, you slightly move your aircraft from away from the ground, from above from the ground, everything is considered in the air loads. So that is like um, uh, initial descents, then partial initial descents, then cruise condition, partial descent, and all those stuff are into the air loads. So now this is like how basically we design the aircraft. So predominant stresses acting on the aircraft, like since this acts like a pressure vessel. So every pressure vessel is designed for hoop and longitudinal stresses, hoop stress and longitudinal. And always the hoop stress is critical, because it is sigma is equal to PR by T, whereas this is by 2T, PR by 2T. So it is half. That is why you say predominantly hoop stresses, hoop impact. Then this is going to bend, torsion, compression, and all the stuff. So these are like various, everybody might have studied in the 11th, 12th, and even first, second, third year of engineering. This goes throughout the life. If you are going to be an aircraft structures engineer, then the basic thing is the basic formula which you need to know, and it is P over A plus MC over I, axial and bending loads. The third is the torsional, but axial and bending is like each and every component will go through axial and bending. So if you are not good at the free body diagram, this is like free body diagram is like a you say a bible. If you don't have know how to draw a free body diagram, it's really difficult to get a to be a good structural analyst. Not even a good, you can't be a structural analyst first thing if you don't know how to draw a free body diagram, if you don't know how to resolve the forces, all the stuff. So now, okay, if you don't know that, it's okay, but these days your life is easy because you get the softwares where you just applied the loads. Somebody provides you the loads group will provide you the load, and you apply the loads, and the pattern Nastan, the solver, generates all the loads for you, elemental, because it has all the theory inside it. So you need not memorize it, or you need not what we say by heart those theories. You can always have a handwritten notes or saved copies of the theories at your go to read, because behind the theory you can't, I mean to say, without knowing the theory you can't know what if I am going to have a more I'm to say, if I want to fly this aircraft at 35,000 feet and I want to have a comfort level of 5,000 feet, then the stresses will be predominant on this fuselage. The same aircraft, if I'm going to fly at 35,000 feet, it is within the same environment, and I want to maintain a cabin pressure of 8,000. This is going to have a lesser load. So somebody should know. This structures analyst should be aware about that. What is going through that loads, how it is going. Okay, then I can make this structure thinner. I'm going to say less beefier, or I can reduce the weight. This is the theory, like because it's a PR by T. So your pressure is you're changing the pressure. R and T are constant. That's how. Now this is like a basic aircraft structures design, conceptual design, basic understanding of how the part should be arranged. Should you want, do you want to have a double engine, I'm going to say 4 engines, or 2 engines are fine? Do you want to have a spoiler, I'm going to say flap track, with the flap track fairings or without a flap track fairings? This is like conceptual design engineering, like what should be the shape, size, and all those stuff. But this is a very raw ribbon. It is like if somebody wants to design the aircraft in 2035, then the conceptual should be ready by now, because it takes minimum 3 to 4 years for a structures analyst, a team of like 70% team of your budget, to analyze that from preliminary design to detailed design. It's preliminary design, you've analyzed all your things, like okay, what will be the weight and all those stuff, what engine, what fuel, what will the cost, and all those stuff. So from here to here it takes 3 to 4 to 5 years for a structures to freeze the things. So there is a lot of amount and a lot of money spent on the structures design, because that is, if if anything on here, I don't say that single frame or single rib fails the whole aircraft. No, no, it won't fail, because we design in such a way that even if fails, this two adjacent ribs will carry the additional loads. We design it in that way. It will be uniformly distributed in the parabolic or hyperbolic way or elliptical way. But you can't say that okay, both the engines are failed. No, no, that can't be the thing. So there are certain things like landing gear. We cannot you cannot design you cannot have two landing gears. If one landing gear is failing, it's failed. That's how the structure is designed. They call it as a safe life. So if once the life is over, stop it. And another is fail safe. For example, even if this is failed, if I say this rib is failed, it's still safe to fly the aircraft. So we call it as a fail safe design. So all these are fail safe designs. Whole structures we design it as a fail safe, except a landing gear. And I would say, trust me, if somebody can solve landing gear problem, he can solve most of the structural problems, because landing gear will have a three-dimensional loading. Except this will have a 2D loading predominantly. So now this is like a small demo, which, yeah, this is like a small hypermesh, like what we are going to do with the hypermesh. Like this is Generally, this is a CATIA geometry. We import it in the Hypermesh and we mesh it. So there are various way of meshing, like composite meshing is a totally different, metallic meshing is totally different. What is the thickness? What are the load conditions? What are the boundary conditions? What material, how you should mesh it, and all the stuff. It is a totally different topic than aero structures. Until and unless you don't know what is the how to get a free body diagram, or how to get how to get the shear force and bending moment diagram for that wing manually, it's really difficult for you. Even you can be a good mesher, but you can't be a good analyst. There is a difference between somebody who is good at meshing and throwing the results, and somebody who is understanding what is going behind. Because if something, the problem comes, you have to rectify it. So Hypermesh is a tool where you can uh, break down your geometry. Like for example, this wing, complete wing, you can break down it like just like a pattern. You can break down it because these tools are mathematical tools. For this complete wing, I break down a small panel. Okay, this panel I fixed it here, and I fixed it here because it's a small panel coming out from the wing, and there are few ribs coming out there, and few ribs coming in this direction also. So I have just meshed this and applied the boundary conditions, like what are the loads, where I have to fix it, what should be the degree of I'm going to say how many degree of freedoms I should give to each and every element. I have to define it. So once you define it, you run it into the Nastran, because in aircraft structures we still don't believe OptiStruct as an hypermesh solver. I'm going to say no. I'm going to say the ISA or FAA, or you call Japanese aviation body JAR, they don't approve OptiStruct results still now for structural analysis. They approve only pattern Nastran results. Nastran is a solver and Hypermesh is a preprocessor, which we use it. If you do the same thing in the pattern, it's really, if I take eight, if I take 16 to 24 hours to mesh this component in a Hypermesh, I will take minimum 5 to 10 times time of what I'm going to take in the Hypermesh in the pattern. It's that complex and that rigid to mesh it in the Hypermesh in the pattern. Sorry. So like earlier, we used to, if there is a small changes, we used to edit it in the BDF itself. There are like BDF files from the Nastran, so we edited it in the BDF rather than opening the pattern and changing it in the pattern. So that is also another way of meshing or another way of modifying your geometry, but it should be created before. Here you can create it and you can do it. It's a fast and efficient. That's why we use Hypermesh these days rather than pattern. And that's it. Like this is like uh, job opportunities. Like if you are a good structural analyst by theory, and if you have a tool knowledge which you can gain it by doing any of the courses, or if you have the say if somebody can guide you to how to what element, why we are meshing like this, why we are doing that, then it's not difficult to land a job for you if you have a good theoretical knowledge also along with the meshing. But if you don't have both, then it's really tough. And then that's it from my side, folks.